In electromagnetism, the concepts of vector cross product, outer product, and dot product, inner product, are important. These two operations aid in understanding the properties and directions of vectors and are utilized in various fields of electromagnetism. 1. Cross product. The cross product is an operation that generates a new vector composed of the perpendicular components of two vectors. It is commonly used to describe physical quantities such as force, moment, and magnetic fields. The cross product of vector A and vector B is denoted as A times B. The resulting vector possesses the following characteristics. Magnitude: vertical bar A times B vertical bar equals vertical bar A vertical bar B vertical bar sine theta, where vertical bar A vertical bar and vertical bar B vertical bar represent the magnitudes of vector A and vector B, respectively, and theta is the angle between A and B. Direction, determined using the right-hand rule. In the plane from A to B, the direction of the cross product vector is indicated by the direction of the thumb of the right hand. The cross product is important because it yields a vector with both magnitude and direction, creating a vector perpendicular to the two input vectors. It is used to explain torque, rotational motion, magnetic properties, and more. 2. Dot product. The dot product is an operation that calculates the product of two vectors and returns a scalar value. The dot product is employed to determine the similarity between two vectors or to compute vector magnitudes, angles, projections, and more. The dot product of vector A and vector B is denoted as A middle dot B. The resulting value is calculated as follows. A middle dot B equals vertical bar A vertical bar B vertical bar cosine theta, where vertical bar A vertical bar and vertical bar B vertical bar represent the magnitudes of vector A and vector B, respectively, and theta is the angle between A and B. The dot product possesses the following important properties. When two vectors are parallel, the dot product reaches its maximum value. In the case of completely aligned directions, the dot product becomes vertical bar A vertical bar B vertical bar. When two vectors are orthogonal, perpendicular, the dot product is 0. Orthogonal vectors have a dot product of 0, indicating no correlation between the two vectors. The dot product is influenced by vector magnitudes and angles. Smaller magnitudes or smaller angles result in smaller dot product values. The dot product is related to vector projection. The magnitude of vector A projected onto vector B can be obtained using the dot product. The dot product plays a significant role in electrical work, energy calculations, the cosine rule, and more. For example, in electrical circuits, the dot product of voltage and current vectors is used to compute power. Additionally, the dot product is utilized to assess the similarity between vectors. The closer the dot product of vectors A and B is to 0, the more distinct their directions are. Therefore, the concepts of vector cross product and dot product are essential in electromagnetism, aiding in understanding vector properties and directions.
Scalars are used in conjunction with vectors to represent the magnitude, scale, of a vector or to perform scalar multiplication, which involves multiplying a vector by a scalar value. Scalar multiplication alters the size of a vector. For example, when multiplying a scalar value of 3 with a vector, 2, 4, the result is 6, 12. When the scalar value is positive, the direction of the vector remains unchanged, while only the magnitude changes. When the scalar value is negative, the direction of the vector reverses along with the magnitude. Scalars are utilized in various fields such as physics, mathematics, computer science, and more. They are commonly used to represent quantities without a specific direction, such as size, mass, time, temperature, density, etc. Scalars also play a significant role in vector operations such as scalar multiplication, scalar product, dot product, etc. To summarize, a scalar represents a quantity with magnitude only and no direction. Scalars are used in conjunction with vectors to indicate magnitude or perform multiplication operations. Sure, let me provide a translation of the content. Scalars are an important concept in electromagnetism. Scalars are quantities that have only magnitude and no direction. They are commonly used to represent physical quantities such as temperature, mass, charge, energy, and time, which do not have a specific direction associated with them. In electromagnetism, scalars are used in various calculations and equations. For example, when calculating the electric potential at a point in an electric field, We use scalars. The magnitude of an electric field at a point is also a scalar quantity. Scalars are also used in vector calculus. When taking the gradient of a scalar function, we obtain a vector that points in the direction of the steepest increase of the scalar function. In summary, scalars are quantities that have only magnitude and no direction. They are widely used in electromagnetism, vector calculus, and other fields of physics to represent various physical quantities.
Here is the explanation of vector cross product and dot product calculations with examples. 1. Cross product calculation example. Let's calculate the cross product of vector A equals 2, 3, 4, and vector B equals 5, minus 1, 2. A times B equals vertical bar A vertical bar B vertical bar sine theta, n. First, we calculate the magnitude of the cross product. Vertical bar A times B vertical bar equals vertical bar A vertical bar B vertical bar sine theta. Vertical bar A vertical bar equals 2 squared plus 3 squared plus 4 squared, equals 29. Vertical bar B vertical bar equals 5 squared plus, minus 1 squared plus 2 squared, equals 30. Theta represents the angle between the two vectors, and we can calculate it using the dot product. A middle dot B equals vertical bar A vertical bar B vertical bar cosine theta. A middle dot B equals 2 times 5 plus 3 times minus 1, plus 4 times 2 equals 6. Cosine theta equals a middle dot B. Vertical bar A vertical bar B vertical bar equals 6, 29 30, 0.303. Therefore, sine theta equals 1, cos squared theta equals 1 to 0.303 squared, 0.953. Now we can calculate the magnitude of the cross product. Vertical bar A times B vertical bar equals 2930 times 0.9536.98. The direction of the cross product is determined using the right-hand rule. In the plane from A to B, point your right-hand thumb in the direction of A, and the cross product vector will point in the direction of your fingers. Therefore, the cross product of vector A and vector B, slightly normalized, would be approximately 0.877, 3.13, minus 17.4, values rounded to decimal places. 2. Dot product calculation example. Let's calculate the dot product of vector A equals 2, 3, minus 1, and vector B equals minus 4, 1, 5. A middle dot B equals vertical bar A vertical bar B vertical bar cosine theta. Vertical bar A vertical bar equals 2 squared plus 3 squared plus, minus 1 squared, equals 14. Vertical bar B vertical bar equals minus 4 squared plus 1 squared plus 5 squared, equals 42. Theta represents the angle between the two vectors, and we can calculate it using the dot product. A middle dot B equals 2 times minus 4, plus 3 times 1 plus, minus 1 times 5 equals minus 6. Cosine theta equals a middle dot B. Vertical bar A vertical bar B vertical bar equals minus 6, 1442, minus 0.341. The vector 2, 3, 4 represents the components along the x, y, and z axes, respectively. In three-dimensional space, vectors typically have components in the x, y, and z directions, and they are represented in the x, y, z form. Here, the x, y, and z axes refer to the coordinate axes. Usually, the x-axis represents the left-right direction, the y-axis represents the up-down direction, and the z-axis represents the front-back direction. By expressing a vector in terms of its components, we can interpret it as indicating how much movement occurs in each axis direction as coordinate values. Therefore, the vector 2, 3, 4 indicates a movement of 2 units in the x direction, 3 units in the y direction, and 4 units in the z direction. These coordinate values can be used to represent the position or displacement vector of an object, among other applications. In the vector b equals 5, -1, 2, the -1 represents the component along the y-axis. The y-axis typically represents the vertical or up-down direction, where positive values indicate upward movement and negative values indicate downward movement. Therefore, when the y component of vector b is -1, it signifies a movement of 1 unit in the negative y direction, indicating a downward movement along the y-axis. Please understand that the y-axis represents the vertical or up-down direction, while the x-axis represents the horizontal or left-right direction. Generally, the x-axis represents the left-right direction, and the y-axis represents the up-down direction. Therefore, the components of a vector can be interpreted as indicating the amount of movement in the x direction, horizontal, and the y direction, vertical. For example, the vector 3, -2, implies a movement of 3 units in the x direction, to the right, and -2 units in the y direction, downward. Hence, the y-axis represents the up-down direction, and the x-axis represents the left-right direction in the conventional notation.
The z-axis typically represents the forward-backward direction. Generally, the x-axis represents the left-right direction, the y-axis represents the up-down direction, and the z-axis represents the forward-backward direction in a coordinate system. Moving in the negative direction of the z-axis corresponds to moving backward, while moving in the positive direction represents moving forward. Therefore, the positive component of the z-axis indicates the amount of forward movement, and the negative component represents the amount of backward movement. In terms of coordinates, the positive direction of the z-axis points outward from the screen, while the negative direction points inward toward the screen. For example, a vector 2, 1, -3 means moving 2 units in the x-axis direction, 1 unit in the y-axis direction, and -3 units in the z-axis direction. This can be interpreted as moving 2 units to the right, 1 unit upward, and 3 units backward. To clarify, the cross product is an operation that generates a vector with both direction and magnitude, rather than just an area. The cross product allows you to obtain a new vector from the cross product of 2 given vectors. In this case, the resulting vector aligns with the normal vector of the plane formed by the 2 vectors and shares its direction, while its magnitude is proportional to the area of the parallelogram formed by the 2 vectors. Therefore, the resulting vector from the cross product has both direction and magnitude, and it points perpendicular to the plane formed by the original vectors. For example, the cross product of vector A and vector B, denoted as A times B, creates a new vector C. This vector C aligns with the normal vector of the plane formed by A and B and shares its direction, while its magnitude is proportional to the area of the parallelogram formed by A and B. The magnitude of the resulting vector from the cross product is calculated as follows. A times B equals A, B, sin, theta. Here, A and B represent the magnitudes of A and B, and theta is the angle between A and B, hence, the magnitude of the resulting vector from the cross product is proportional to the product of the magnitudes of the 2 vectors and the sine of the angle between them. The cross product is defined for 3-dimensional vectors, and the resulting vector is determined using the right-hand rule to determine its direction. In summary, the cross product is an operation that generates a new vector from the cross product of 2 given vectors. This resulting vector aligns with the normal vector of the plane formed by the original vectors, shares its direction, and its magnitude is proportional to the area of the parallelogram. When the angle between 2 vectors is 90 degrees, their cross product results in a new vector, and when the angle is 0 degrees, the cross product yields a 0 vector. When the angle between 2 vectors, A and B, is 90 degrees, they are orthogonal to each other. The magnitude of the cross product, A times B, is given by A, B, sin, theta, where sin, 90 degrees, equals 1. Therefore, the magnitude of the cross product is equal to A, B. Hence, if the magnitude of the cross product is non-zero, the resulting vector is perpendicular to both vectors A and B. On the other hand, when the angle between two vectors, A and B, is 0 degrees, they are parallel to each other. The magnitude of the cross product, A times B, is given by A, B, sin, theta, where sin, 0 degrees, equals 0. Therefore, the magnitude of the cross product becomes 0. As a result, the cross product yields a 0 vector. This indicates that the two vectors are pointing in the same direction and are parallel to each other. In conclusion, when the angle between two vectors is 90 degrees, the cross product generates a new vector, and when the angle is 0 degrees, the cross product results in a 0 vector. The dot product of two vectors is indeed related to the angle between them. When the angle between two vectors is 90 degrees, the dot product is 0, and when the angle is 0 degrees, the dot product equals the product of the magnitudes of the vectors. 1. When the angle is 90 degrees, perpendicular case, if two vectors A and B are perpendicular to each other, the dot product AB is 0. This is because the dot product represents the projection of one vector onto the other, and when the vectors are perpendicular, their projections are 0. Mathematically, AB equals AB, cos, theta, and when the angle is 90 degrees, cos, 90 degrees, equals 0, resulting in a dot product of 0. This indicates that the vectors are perpendicular or orthogonal to each other. 2. When the angle is 0 degrees, parallel case, if two vectors A and B are parallel to each other, the dot product AB equals the product of their magnitudes. The dot product measures how much the vectors are aligned in the same direction. When the angle is 0 degrees, cos, 0 degrees, equals 1, so the dot product becomes AB. This means that the dot product is equal to the product of the magnitudes of the vectors because they have the same direction. The dot product can be used to measure the similarity or alignment of two vectors. Therefore, when the angle between two vectors is 90 degrees, the dot product is 0, and when the angle is 0 degrees, the dot product equals the product of the magnitudes of the vectors. The dot product is a crucial concept that helps determine the orthogonality or parallelism of vectors. The dot product is defined by the following equation. AB equals AB, cos, theta. Here, A and B are two vectors, and A and B represent the magnitudes, lengths, of vectors A and B, respectively. Theta denotes the angle between the two vectors. The dot product yields the product of the magnitudes of the vectors multiplied by the cosine of the angle between them. It measures how much the vectors align in the same direction. If the result is positive, the vectors have a similar direction, and if it's negative, they have opposite directions. On the other hand, the magnitude of the cross product, not the cross product itself, is given by the following equation. A times B equals AB, sin, theta. Here, A and B are two vectors, and A times B represents the magnitude of their cross product. Theta denotes the angle between the two vectors. The cross product results in a vector that is perpendicular to the plane formed by the two vectors and has a magnitude proportional to the area of the parallelogram formed by the vectors. The cross product carries directionality, pointing in the direction of the normal vector to the plane formed by the original vectors. Therefore, the correct equations related to the dot product and the cross product are as follows. Equation for the dot product. AB equals AB, cos, theta. Equation for the magnitude of the cross product. A times B equals AB, sin, theta.
Let's calculate the cross product and dot product using the given example. Assuming an angle of 45 degrees, theta equals 45 degrees, we have the following vectors. A equals 2, 3, 4. B equals 5, minus 1, 2. First, let's calculate the cross product, A times B. A times B equals A underscore Y asterisk B underscore Z, A underscore Z asterisk B underscore Y.
A underscore Z asterisk B underscore X, A underscore X B underscore Z, A underscore X B underscore Y, A underscore Y asterisk B underscore X. Equals 3 asterisk 2, 4 asterisk, minus 1, 4 asterisk 5, 2 asterisk 2, 2 asterisk, minus 1, 3 asterisk 5. Equals 6 plus 4, 20 to 4, 2 to 15. Equals 10, 16, minus 17. Therefore, A times B equals 10, 16, minus 17. Now, let's calculate the dot product, AB. AB equals AB, cos theta. Equals square root 2 squared plus 3 squared plus 4 squared, asterisk square root 5 squared plus, minus 1, squared plus 2 squared, asterisk cos, 45 degrees. Equals square root 4 plus 9 plus 16, asterisk square root 25 plus 1 plus 4, asterisk 0.7071. Equals square root 29 asterisk square root 30 asterisk 0.7071. Equals 5.3852 asterisk 5.4772 asterisk 0.7071. Approximately equals 19.2816. Therefore, AB approximately equals 19.2816. By calculating the cross product, we find that when the angle is 45 degrees, the resulting vector is 10, 16, minus 17. And by calculating the dot product, we find that it is approximately 19.2816 when the angle is 45 degrees. Thus, we have computed the cross product and dot product using the given example. The dot product of vectors is an undirected scalar value. It represents the magnitude of the vector's similarity in direction. The result of the dot product solely indicates the magnitude and does not carry any directional information. The dot product is used to measure how much two vectors align with each other. If the result is positive, it means the vectors have a similar direction, while a negative result indicates they have opposite directions. If the result is 0, it means the vectors are orthogonal, perpendicular, or one of the vectors is the zero vector. The dot product is determined by the magnitudes and the angle between the vectors. The magnitude of the vectors affects the value of the dot product, as does the angle between them. However, the dot product itself does not possess directionality. It is solely a value associated with the magnitudes of the vectors. The cross product of vectors represents a vector with a specific direction. The result of the cross product is a new vector that possesses directionality. It follows the right-hand rule to determine its direction and points towards the normal vector of the plane formed by the two vectors. The magnitude of the cross product is proportional to the area of the parallelogram formed by the two vectors. On the other hand, the dot product of vectors is an undirected scalar value. The result of the dot product simply indicates the magnitude and does not carry any directional information. The dot product is used to measure how much two vectors align with each other. If the result is positive, it means the vectors have a similar direction, while a negative result indicates they have opposite directions. If the result is 0, it means the vectors are orthogonal, perpendicular, or one of the vectors is the zero vector. Therefore, the cross product yields a vector with direction, while the dot product yields an undirected scalar value. Yes, that's correct. The multiplication of vectors is performed element-wise. Therefore, the product of A, B, C, and X, Y, Z vectors is calculated as follows. A, B, C, times X, Y, Z, equals A asterisk X, B asterisk Y, C asterisk Z, equals X, by, CZ. The resulting vector is formed by the multiplication of corresponding elements, and the order of the elements remains the same. Hence, the product of A, B, C, and X, Y, Z can be represented as X by CZ. Problem: calculate the cross product and dot product of the two vectors A equals 2, 3, 4, and B equals 5, minus 1, 2. Solution: 1. Cross product, A times B, calculation. A times B equals A underscore Y asterisk B underscore Z, A underscore Z asterisk B underscore Y, A underscore Z asterisk B underscore X, A underscore X B underscore Z, A underscore X B underscore Y, A underscore Y asterisk B underscore X equals 3 asterisk 2, 4 asterisk minus 1, 4 asterisk 5, 2 asterisk 2, 2 asterisk minus 1, 3 asterisk 5 equals 6 plus 4, 20 to 4, 2 to 15 equals 10, 16, minus 17. Therefore, A times B equals 10, 16, minus 17. 2. Dot product, AB, calculation. AB equals A underscore X B underscore X plus A underscore Y asterisk B underscore Y plus A underscore Z asterisk B underscore Z equals 2 asterisk 5 plus 3 asterisk minus 1 plus 4 asterisk 2 equals 10 to 3 plus 8 equals 15. Therefore, AB equals 15. In conclusion, the cross product of the given vectors A and B is 10, 16, minus 17, and the dot product is 15. 1. Dot product, AB, calculation. The dot product is calculated as follows. AB equals A underscore X B underscore X plus A underscore Y asterisk B underscore Y plus A underscore Z asterisk B underscore Z equals 2 asterisk 5 plus 3 asterisk minus 1 plus 4 asterisk 2 equals 10 to 3 plus 8 equals 15. The dot product is the sum of the element-wise multiplication of the corresponding components. Therefore, AB equals 15. 2. Cross product, A times B, calculation. The cross product is a vector operation that results in a new vector. It is calculated as follows. A times B equals A underscore Y asterisk B underscore Z, A underscore Z asterisk B underscore Y, A underscore Z asterisk B underscore X, A underscore X B underscore Z, A underscore X B underscore Y, A underscore Y asterisk B underscore X equals 3 asterisk 2 to 4 asterisk minus 1, 4 asterisk 5 to 2 asterisk 2, 2 asterisk minus 1, 3 asterisk 5 equals 6 plus 4, 20 to 4, 2 to 15 equals 10, 16, minus 17. Therefore, A times B equals 10, 16, minus 17. The dot product is a scalar value obtained by multiplying and summing the corresponding components. On the other hand, the cross product is a vector obtained by calculating the pairwise cross products of the original vectors. This resulting vector represents the direction of the normal vector to the plane formed by the original vectors. 1. Dot product, AB, formula. AB equals A, asterisk, B, asterisk cos, theta. In the dot product formula, we use the magnitudes, A, B, of vectors A and B and the cosine value of the angle, theta, between the two vectors. This formula represents a value that indicates how similar the directions of the two vectors are. If the angle theta is 90 degrees, cos 90 degrees equals 0, resulting in a dot product of 0. This means that the two vectors are orthogonal, perpendicular, to each other. Additionally, if the dot product is positive, the two vectors have similar directions, while a negative dot product indicates opposite directions. 2. Cross product, A times B, formula. A times B equals A, asterisk, B, asterisk sin, theta, asterisk n. In the cross product formula, we use the magnitudes, A, B, of vectors A and B, the sine value of the angle, theta, between them, and a unit vector, n, that determines the direction of the resulting cross product vector. The cross product result has a magnitude of A, asterisk, B, asterisk sin, theta, and its direction is determined by n, which is perpendicular to both vectors in the plane. The sin, theta, represents the sine value of the angle between the two vectors. Therefore, the cross product is a vector operation that simultaneously represents both magnitude and direction. To summarize, the dot product uses the cosine value to measure the similarity in direction between two vectors, considering their magnitudes, while the cross product uses the sine value to represent the vector's direction and magnitude, considering the magnitudes and the angle between the two vectors. You are correct that the calculated values in the example and sin, theta, and cos, theta, are different concepts. The calculated values in the example represent the actual results obtained through vector operations, indicating the magnitude and direction of the vectors. These values are computed based on the given vector values and depend on the specific calculation method. On the other hand, sin, theta, and cos, theta, represent the values of trigonometric functions. They represent the sine and cosine values of an angle theta, respectively. In other words, they take on specific values depending on the angle. For example, if theta is 45 degrees, sin, 45 degrees, is square root 2 halves and cos, 45 degrees, is square root 2 halves. The reason why sin, theta, and cos, theta, are used in the formulas for dot product and cross product is due to the relationship between vector operations and trigonometric functions. They help to relate the angle between two vectors to the computed results, representing both the direction and magnitude. Therefore, the calculated values in the example and sin, theta, cos, theta, are separate concepts with different meanings. The calculated values represent the results of vector operations, while sin, theta, and cos, theta, represent the trigonometric values associated with an angle.
The unit vectors I, j, k in the context of vector cross product are typically referred to as follows. I represents the unit vector in the positive x direction. It is commonly denoted as 1, 0, 0. J represents the unit vector in the positive y direction. It is commonly denoted as 0, 1, 0. K represents the unit vector in the positive z direction. It is commonly denoted as 0, 0, 1. These unit vectors define the basis axes of an orthogonal coordinate system in three-dimensional space. The cross product operation, also known as the vector product, utilizes these unit vectors to perform geometric calculations in three-dimensional space. The result of a cross product is a vector that is perpendicular to the plane formed by the two input vectors. Therefore, I times j would yield a vector orthogonal to the xy plane, k direction, and k times I would yield a vector orthogonal to the yz plane, x direction. The cross product of vectors is an irreversible operation, and the result can vary depending on the order of the vectors. Therefore, the results of I times k and k times I can be different. In the context of cross product operations, the reason for the dependence on the order of vectors lies in the definition of the cross product. The cross product of vectors a and b is defined as a times b equals a, b, sin, theta, n. Here, a represents the magnitude of vector a, b represents the magnitude of vector b, theta represents the angle between a and b, and n represents the unit vector perpendicular to both a and b. Therefore, for I times k, considering the angle between I and k as theta, the magnitude of the resulting vector is I, k, sin, theta, and its direction is perpendicular to both I and k. On the other hand, for k times I, considering the angle between k and I as theta, the magnitude of the resulting vector is k, I, sin, theta, and its direction is perpendicular to both k and I. As a result, I times k and k times I can have different magnitudes and directions. The electric field intensity represents the strength of the electric field at a specific location. It indicates the magnitude and direction of the electric force acting on a unit positive charge at that location. The electric field is generated by electric charges, and the electric force represents the magnitude of the force generated by charges. The Poisson's equation is an equation that describes the relationship between the electric field and electric charges. It mathematically expresses the phenomenon where electric forces are generated by charges. The Poisson's equation is represented as squared phi equals rho, epsilon. Here, squared represents the Laplacian operator, which is the sum of the squared partial derivatives. Phi represents the scalar potential of the electric field, rho represents the charge density, and epsilon represents the permittivity of free space. This equation is a differential equation for the scalar potential phi of the electric field, providing a mathematical model for determining the electric field based on the charge distribution. The Laplace's equation is a special case of the Poisson's equation that is used when dealing with the electric field in free space where no charges are present. The Laplace's equation is expressed as squared phi equals 0. This equation represents a differential equation for the electric field intensity at a particular location where there is no charge. It describes the electric field in the absence of charges. The Laplace's equation is an important tool used to determine the distribution of the electric field. The equation E equals nabla V equals V, tau represents a general relationship between electric field and voltage, electric potential. Here, E represents the electric field vector. V represents the voltage, electric potential. Nabla represents the gradient, vector differential operator. Tau is a variable representing time, and in steady-state conditions, it can be considered as tau equals 1 since there is no explicit dependence on time. In the equation, nabla V represents the negative gradient of the voltage V using the vector differential operator. The gradient represents the rate of change in direction of a scalar function, in this case, the voltage. Therefore, nabla V represents the electric field vector E, which represents the spatial rate of change in direction of the voltage. This equation illustrates how an electric field is formed due to the spatial variation of voltage, with the electric field pointing in the direction opposite to the decrease in voltage. Additionally, if E equals V tau is expressed, it implies that tau represents a time constant. This indicates the relationship between the electric field and the changing voltage over time. It signifies that the electric field is formed and varies in response to the changes in voltage over time. Such equations provide a connection between electric fields and voltages, aiding in understanding the characteristics and interactions between electric fields and potentials in electromagnetism.